All right, we've got the last bit of the notes for Chapter 12, 12.6 and 12.7. So as you know, we've kind of transitioned from more of the math to talking more about the theory behind chemical kinetics. This is definitely very theoretical. In fact, we call it collision theory. It's our model for how chemical kinetics works. It's going to show the relationship between the molecularity of a slow step of a mechanism and the rate law. And it's a model called collision theory. Reactions occur because molecules collide, but not all collisions between molecules are successful at resulting in a chemical change. Only the collisions that have the proper orientation of the molecules and when they collide with enough kinetic energy, because you have to get kinetic energy to overcome the potential energy change you need to break the bonds in the reactants so you can form the bonds in the products. So generally it can just be modeled as two molecules collide, or maybe more than two, but whatever. The molecules collide with the proper orientation, and then their bonds break and new bonds form. But to get the energy to break the bond, you have to have kinetic energy in the collision. Now, this model is actually pretty good at explaining things such as, why does concentration affect rate? Well, concentration affects rate because higher concentration means more collisions. More collisions means you'll have a better chance of having the proper orientation and enough kinetic energy. It also explains why raising temperature makes rates go up. So generally, any chemical reaction is always going to be faster if you raise the temperature. And that's because raising temperature means that your molecules have more kinetic energy. So if they happen to collide with the proper orientation, they'll have a better chance of having enough kinetic energy to break the bonds. And finally, it also explains why rates are different for different reactions. So what you can usually tie it back to is some bonds are stronger than others, and so when bonds are stronger, it takes more energy to break them, and so you're less likely to have a successful collision when the bonds are stronger. Which explains why, even though nitrogen and oxygen will react to make nitrogen oxides, you typically don't see the nitrogen and the oxygen in the air becoming nitrogen oxide, because the nitrogen is a triple bond and the oxygen is a double bond. So they can collide over and over and over again, and very rarely do you get the proper reaction collisions that will make nitrogen and oxygen into nitrogen oxides. So one way to kind of understand this model is to look at what happens to the potential energy as the reaction occurs. Now, previously we've talked about how if the reactants have more energy than the products, it's exothermic, and if the reactants have less energy than the products, it's endothermic. But we didn't really show the part of the graph in between the reactant and the products. We just kind of connected the reactants to the products with a straight line. Actually, what the energy of the molecules do is the reactant molecules are somewhat stable because they're bonded. The collision causes the potential energy to go up, and so it like climbs a hill. And the top of the hill would be where the bonds are breaking, because breaking energy raises potential energy. Then, as the new bonds form, the energy goes back down. So if it goes back down more than it went up, you have an exothermic process. If it goes down less than it went up on the left side, you have an endothermic process. But the height of the hill is going to determine how easy it is for a collision to have enough energy to get over the hump. If you have a high energy hill, okay, so let's get some terminology down here. We call the height of the energy hill the activation energy. So if the activation energy is high, then you got to have a lot of collision energy to break the bonds to make before you can form the products. So the activation energy is that energy hump that you have to get over in order to get to the product side. the point of where the bonds are breaking during the collision, that is actually the point of highest potential energy. And on the graph, the highest potential energy point is called the transition state. Some people call it the activated complex because it has enough activation energy to get over the hump. So those are some terms, but that's really what's happening. You're starting with your molecules in the reactant side. They're colliding at the proper orientation with enough kinetic energy. Their kinetic energy becomes potential energy, and they go to the transition state. Then they reorganize to make the products, and their energy comes back down because they form bonds. Now, most collisions don't have enough energy to get over the activation energy hump. Then that's because most of the collisions are going to be molecules with too little kinetic energy. So let's remind ourselves, the Boltzmann distribution graph shows us how much energy the molecules have. And it shows us that some have very little, most are in the middle, and some are on the right at very high kinetic energies. If you have a reaction with a low activation energy, then there are going to be a lot of molecules that have enough energy to match that lower activation energy. A lot more than if your reaction has a higher activation energy. So you can see on this graph, the light brown area, everything to the right of that would represent molecules that collide with enough kinetic energy to make a reaction happen. But the darker brown, the little bit darker brown area, that would be the molecules that would collide with enough energy if you had a higher activation energy. Now, that middle graph kind of illustrates that. Now, if we take a look at the right graph, we see two different curves, one for T1 and another for a higher temperature. So notice at a higher temperature, you have more molecules that are going to have enough activation energy, are going to have enough energy to break the bonds and supply the activation energy needed to get over the hump. And so we're seeing two things here. In the middle graph, we're seeing that if the activation energy of the reaction is high, it's going to be a slow reaction because not many collisions are going to have enough energy to get over the hump. And if the activation energy is low, you're going to have faster reaction because more collisions are going to have enough energy to get over the hump. And then on the right, we're seeing that raising the temperature gives us more molecules that are going to have enough activation energy. So we're seeing the temperature effect, we're seeing the effect of it being different for different reactions, we're seeing the effect of concentration. These are all tied into this model of chemical kinetics. Now, in this model, if we get back to a little bit of math here, Svante Arrhenius, back in the 1880s, proposed this equation for the rate constant. So he said that the rate constant was some pre-exponential factor A, which actually is related to the frequency of collisions that have enough or that have the right orientation, and then E, Euler's number, the base of the natural log, raised to the power of this formula, negative activation energy over R and the temperature in Kelvin, R being the gas constant. So in this formula, you see the relationship between the rate constant and activation energy and temperature. So if you think about it, if the activation energy is higher, the exponent of E is going to be more negative. The more negative the exponent of E is, then the smaller K is. So what we're saying is at high activation energies, you get a low rate constant and you're going to have a slow reaction. But T is in the denominator, so if T is high, then the negative exponent of E is smaller and negative, which makes it closer to 1, and as a result, the K is larger. Now, if you were to measure the K values at different temperatures, and you can do this. You can do experiments at different temperatures. Remember, we can graph them. We can find the K by finding the slope of the straight line. You can graph the natural log of K as a function of 1 over T, 1 over the temperature, reciprocal temperature. And that's because if you take the natural log of both sides of this equation and do some rearranging algebraically, you get the formula. Natural log K equals negative E sub A over R times the quantity 1 over T plus the natural log of A. That's actually in the format of y equals mx plus b if you plot natural log of k as y and 1 over t as x. And your slope of that line is going to be negative E sub A over R. So you can actually use the slope to find the activation energy. And then the ln of A is the intercept. Well, that's just going to be the natural log of k when the temperature is infinitely high, when 1 over t becomes 0. Now, continuing with our model for chemical kinetics here, since a lot of collisions actually do have enough energy to get over the activation energy hump, but the reactions tend to be slower than you might expect based on just those numbers, we realize that there's more than just getting over the hump to form products. You also have to make sure your collision has the proper orientation. So here we have NO colliding with O3. And if you happen to collide head on with your NO, doesn't matter if you hit the O3 with the O or the N, head-on collisions hit right in the middle of the O3 don't do anything to the O3 molecule. However, if you can get a glancing blow, if you can happen to collide with a glancing blow at the proper angle, and if you get the N on the NO to knock the O off of the O3, you can actually get a collision that will make NO2 plus O2. So that's the idea of the correct orientation of molecules. Okay, and now the final section, 12.7, catalysis. Catalysts. These are these weird chemicals that speed up reactions, but they're not reactants and they're not products. So how do they speed up reactions? Well, that's what we're going to learn. Unlike a intermediate, which is on the right and then later on the left, a catalyst occurs on the left side of the equation and then later on the right. So a catalyst actually acts like a reactant in an early step, but then becomes a product in a later step. So it's like it's used for a while during the reaction to make the reaction faster, but then it gets regenerated. It's reformed by the end of the reaction. So when you add all the steps of a multi-step mechanism together, the catalyst is not on either side. Now it was on one side during an early reaction step and then on another side during a later elementary step. And so that's why it cancels out in the equation. So if you said A plus X makes this AX intermediate, and then the AX intermediate collides with B to make AB plus X, the overall reaction would be A plus B yields AB. X is not a reactant and it's not a product, but X participated in the mechanism and in fact helped the reaction to go faster. So an enzyme would be an example of a biological catalyst. Let's say you've got an enzyme, it's got an active site, you've got a substrate, the substrate fits into the enzyme's active site, it undergoes a chemical change, and then is released by the enzyme as a changed product. The substrate has been changed to the product because it was absorbed for a while by the enzyme. So notice the enzyme is on the left and the enzyme is regenerated on the right and capable of doing the reaction again. So that's one thing about catalysts. They're not consumed. They're continually available to keep doing the reaction over and over again, and they help speed up reactions. If the catalyst has the same state of matter, like if both are gases, as the reactants, then you say it's homogeneous catalysis. So this is actually illustrating what happened to the ozone layer when the CFCs, the chlorofluorocarbons that we used to use for Freon for our refrigerators and air conditioners, was breaking down the ozone layer. So the CFCs, they escape from the refrigerators, old refrigerators and air conditioners, and they get into the atmosphere. And then ultraviolet light causes a chlorine atom to be knocked off of the CFC molecule. Well, now that chlorine atom acts as a catalyst to take an oxygen off of ozone. And then the oxygen, free oxygen atom can collide with the OCl molecule and make O2. And in the effect, what you've done is you've gotten rid of ozone and you've formed O2. But without the chlorine there, the reaction would actually have been very slow. But with the chlorine present, it was actually happening quite a bit faster, and that's why it was generating an ozone hole over the South Pole. So this free chlorine, notice on the right in step 5, it's back to being a chlorine atom. It could do the thing again. It could do the reaction again. It's a catalyst. But the chlorine atom is a gas. The ozone's a gas, so we call it homogeneous catalysis. It's possible for a molecule of a gas to stick to a solid surface and undergo a chemical reaction while sticking to the solid surface. That would be an example of heterogeneous catalysis, because the catalyst is a solid surface and the gas is, of course, in the gas phase. So an example of this would be maybe the addition of hydrogen to the ethylene molecule to make the ethane molecule C2H6. So what might happen was the hydrogen molecule would stick to maybe a surface of a metal, and then that would cause the hydrogen bond to hydrogen single bond to break, and the hydrogen atoms would be bonded to the metal. And then they could move around on the metal surface, and if the C2H4 molecule stuck to the metal, then they would be able to move onto the C2H4 and become C2H6. So the reaction is much faster to make C2H6 out of C2H4 plus H2 if you have that metal surface, if you have that heterogeneous catalyst. Now, catalysts work in one of two ways. They're either going to make your transition state lower in energy, in other words, they're going to stabilize the transition state, which lowers the activation energy, which means more collisions are going to have enough energy to get over the hump, and so the reaction is going to be faster. Or they provide an alternative pathway for the reaction, and the alternative pathway has a lower activation energy. So if we look at the first graph on the left, we see that the blue would be the activation energy if you didn't have the catalyst, and the red is the activation energy if you do have the catalyst. But the shape of the curves is both the same. It's the same reaction. It's just you've lowered the energy, activation energy, by stabilizing the transition state. And so something about the molecule being there makes the transition state more stable. Now, on the other graph, the larger graph in the lower right, we see that X and Y are becoming Z, but in black we see that it would be a one-step process if we didn't have a catalyst, but the catalyst actually creates like 1, 2, 3, 4 humps. Those would be like 4 elementary steps. And then those 4 elementary steps add together to get the overall reaction to form Z. But even though one step becomes 4, it's actually faster because the 4 steps all have lower activation energy than the one step did. Okay, so there are the notes for Chapter 12.